Okay, welcome back. So I've created one that we can do. We can do this one a couple of different ways. So I'm going to do this one, and I'll tell you, this one can be done in two different ways. So that's why it's a nice one to use, because I'm going to show you both ways. So generally, if we're going to do a replacement on something, you're going to take, the most complicated thing and do a replacement on it. So this one we could replace the entire numerator, or we could replace just the radical. And so I'm going to just replace the radical. So I'm going to say, I'm going to let u equal the root of x plus 1. Okay, so I'm going to go back over here and do some rewriting. Uh-oh, I'm running out of space. And so what we could do is we could say that means fine, fair enough. We're going to say then that this is the limit. And I know this is going to have to be a u because there's not going to be any x's left in a moment. So I'm going to replace this, the root of x plus 1 minus 1 with just the u, because that's what we've done. And so the numerator is going to be u minus 1. Now I need to replace this x. So what I can do is I can solve for x in this expression. So I'm going to square both sides, move the 1 over, it's going to be minus 1. So I can see that x is going to be equal to u squared minus 1. So I can come back here and say, haha, this is going to be u squared minus 1. Now, I need to know what value goes in here. Now, the easiest way to do it is just to say, for me, the easiest way to do it is say, well, it used to break, it still needs to break. What value does u break at? I'm going to say it's 1. But, the more official way certainly is to say, well, we've got this expression for u in terms of x. So go and take this 0, put it in for x. 0 plus 1 is 1. Square root of 1 is 1. So that's why u is 1. So we're going to come back here, and we're going to do this really small so we've got room to do it. So we're going to have the limit as u tends to 1. And now I can see there's the difference of squares, right? So it's going to be u minus 1 over u minus 1 times u plus 1. And I can divide through, and I'm going to say for u not equal to 1. And then this is going to become the limit as u tends to 1 of 1 over u plus 1. And now we're in the position that we can actually evaluate that limit. If I substitute the 1 in, it's not going to break, right? So we're going to do the limit, and we're going to evaluate the limit. I'm going to put in the 1. 1 plus 1 is 2, so it's going to be equal to a half. And there it is. Okay, now the alternative method, how much space do we have over here to the right? Hopefully a bit more. Not a ton. Okay, I'll write it really small. So I'm going to grab a different color here. So we could have done this differently. We could have said the same, had to start with the same expression. So we've got the limit as x tends to 0 of the root of x plus 1 minus 1 over x, okay? And so this is another case here. So what are we up to? This was number 4, I think. So this is going to be the 5th way. Another way, so this is kind of case 5, is we can do it by, sometimes conjugation works, right? So conjugating. So I'm going to conjugate this numerator. So if I conjugate this, we're going to have the root of x plus 1 over the root of x plus 1 plus 1. So why would I do that? Well, let's check and see. The limit is x tends to 0. The root of x plus 1 times the root of x plus 1 is, of course, just x plus 1. And then we're going to have a positive version of the root and a negative version of the root. They're going to add up to 0. And then negative 1 times 1 is minus 1. And that's going to be over x times the root of x plus 1 plus 1. Okay, now x plus 1 minus 1 is x. So this x and this x are going to cancel. Those are already gone. So I'm going to be left with just 1 in the numerator. So this simplifies to be the limit as x tends to 0 of, what are we going to have here? We're going to have 1 over the root of x plus 1 plus 1. And now there's nothing stopping me from substituting that 0 in. So we're going to have 1 over the root of 0 plus 1 is 1. The root of 1 is 1. 1 plus 1 is 2. And there it is as a half. So that's kind of a summary of all of the different ways that we can evaluate limits. Okay. The other way that the replacement comes into play, I haven't done an example of this, but you can look in your notes, is sometimes if there are odd powers, right? If there are odd powers, what we would do is we would normally replace the smallest power. So if you had rational exponents, imagine that you had somewhere, an x to the 8th and an x to the quarter, you would want to do a replacement on the 1/8. You do something like, oh, I'm going to let u equal x to the 1/8. And so then this would be u over, well, 1/4 is 2 times 1/8. So that would end up being actually u squared, right? So then we could do some simplification. So the other way when we're doing a replacement is you always want to try and replace the lowest exponent, and then the higher exponents become a higher power, okay? So I'm going to grab, actually, I'm going to maybe just resize this, make this longer. Not keep the same ratio. Let's go down to like 8,000. Hopefully it doesn't go crazy. Maybe it will. Did I not hit OK? Resize. Apparently not. 8,000. Or is that going to be out of scope? Okay. Okay, so I'm going to save this. File, save as, and this is going to simply be called, I'm going to make it a JPEG so those children who want a copy of it later, we're going to call this Calc Review 1. And that's what it looks like, lovely. And then File, New. All right, okay, so here we go. So what's up next? We've done our limits and we did first principles. We did all the different subsections of replacement. So let's go and look at Google Classroom here and see what other information that we have actually played with. That's an old one. Let's go to the new one. So calc and vectors, scan down. Trying to remember if we jumped right into differentiation right after that or we did something else. I think we kind of did something else, but I don't remember for sure. Derivative rules, product rules. No, I guess we got right into derivative rules. Okay. Quotient rule. Yep. All right. So on to some derivative rules. Okay. So calc review continued. I like that color. What color is that? Blue, purple, pink? I don't know. Something nice. Calc review 2. Let's talk about the different rules. So we talked about the product rule. We talked about the quotient rule, but I'm never going to make you do quotient rule. So that one, for me, is going to be strictly optional. And as I've suggested before, Mrs. Whitty loves it. But there are some universities that when you take calculus there, they don't even talk about the premise of a quotient rule. And then there's other ones like the power of a function rule, but the other big one, of course, is going to be chain rule. Those are the biggies that we need to know how to do. So the product rule, quotient rule, I'm not even going to talk about it, or maybe I'll do an example of it. But the chain rule is kind of the 800-pound gorilla because we do that one a lot. So I think the easiest way to do this is just to talk about some examples of this. So let's look at some examples. So imagine that I said f at x is going to be equal to, how about if we had, let's do a simple one. So 6x plus 5 to the 4th times 3x minus 7 to the 5th. And I want to determine f prime at x. Okay, so here we go. So f prime at x. So this is going to be my first, and this is going to be my second. So the product rule says it is the derivative of the first times the second plus the first times the derivative of the second. All right, well, the derivative of the first. Now, if you need to, by all means, you can go off to the side and you could say, 1 prime as in the derivative of the first. And you could just differentiate this piece. You could say, all right, the 4 is going to come down. The 6x plus 5 is going to stay the same. The 4 is going to become a 3. And then actually we're going to have to do chain rule with this as well, or power of a function rule. We're going to multiply by the derivative of the brackets, which is going to be 6. Okay, so simplify that a little bit. It's going to be 24 6x plus 5 cubed. And then you can do 2 prime, because we know we have to differentiate that as well. Same deal. 5 is going to come down. 3x minus 7, I'm going to decrement that by 1, takes me to the 4th, multiply by the derivative of the brackets, which is 3. So that is 15, 3x minus 7 to the 4th. Now, we're probably proficient enough. We don't need to do that anymore. But if you want to do it off to the side to keep things cleaner, have at it. So back we are here. So we're going to do the derivative of the first. We got it right there. So the derivative of the first is 24 6x plus 5 cubed times the second, which is, not modified at all. It's just straight up times the second, not plus, minus. 3x minus 7 to the fifth, plus the first, again, not differentiated, just the first, 6x plus 5 to the fourth, times the derivative of the second. Well, we did that over here. So that's going to be times 15 bracket 3x minus 7 to the fourth. Okay. It's not often this piece that trips students up. It is the factoring and simplification. So we're going to look for all of our greatest common factors. So 24 and 15 is a greatest common factor of 3. So I can pull out a constant of 3. They both have 6x plus 5. This one has 3 of them. So we're going to get 6x plus 5 cubed. And they both have 3x minus 7s. This one has 4 of them as our limiter. So 3x minus 7 to the fourth. All right, so let's pull those pieces out. So 24 divided by 3 is 8. We had 3 of the 6x plus 5s. Took them all. There's none left. We had 5 of these guys. We took 4 of them. So there's one of those left. So we're going to have 3x minus 7. And I could say to the 1, but you know that. Plus 15 divided by 3 is 5. 6x plus 5, we have 4 of them. We took 3 of them. So we're left with one of those guys. So 6x plus 5, of course, to the 1. And then 3x minus 7 to the fourth. I took all of them. So that's it. Right? So we're not going to stop there because we can do some simplification over here. So we're going to have 3 bracket 6x plus 5 cubed times 3x minus 7 to the fourth. And I'm going to distribute and do some simplification here. So we're going to get 24x minus 56 plus 30x plus 25. Most of the way there. Fully simplify. 3 bracket 6x plus 5 cubed times 3x minus 7 to the fourth. And then 24x plus 30x is 54x. Negative 56 plus 25, it's going to be negative 31, I think. Negative 31. Now, negative 31 is prime if I've added that up properly, so I can't simplify that any further. And there it is. That's our derivative. Okay. Way back, simple derivative. Okay, let's try another one. How about if we did one that we could do with quotient rule, but a lot of you would elect to do it with product rule? Again, I'm not going to mandate one way or the other. You can do it however you choose. So imagine that we had, in this case, g at x is going to be equal to, 4 minus 3x to the fifth over 7x minus 2 to the, 10th. Make it big. All right, so from here, we could either break into quotient rule, or we could pull this up and make it a product rule question. Either way, perfectly acceptable. I think in these ones, probably quotient rule is marginally easier, but I don't know. I'm gonna go product rule with this one. So I'm gonna rewrite it, and we're gonna say, all right, this is 4x, or no, that's not. So it's gonna be, 4 minus 3x to the fifth. So that one doesn't get modified at all. Times 7x minus 2, this time to the negative 10th. So again, we're going to do product rule on this guy. I'm off to the side because I want to do this. I'm going to say the first one's prime is going to be, I can do it in 2 steps. So the 5 is going to come down. There's going to be a negative 3, so it's going to be negative 15 bracket 4 minus 3x to the fourth. Okay, and then 2 prime is going to be, the negative 10 is going to come down. It's going to get multiplied by 7, so negative 70. And then this is going to be 7x minus 2. That's where we have to be careful. Negative 10, we decrement, doesn't become negative 9, becomes negative 11. Negative 11. Okay, so back to this. So this is still g at x. So we're going to, did I communicate that properly in the last one? I don't know if I did. Yeah, I did. Okay. So this is still g at x. So I didn't have to write anything here, and we assume that it's g at x. And now, if I'm going to differentiate, which I am, I need to say that I'm differentiating. So this is g prime at x. Okay, so g prime at x. So it's going to be the derivative of the first. Got it right here. So the derivative of the first is negative 15 bracket 4 minus 3x to the fourth times the second. Second is unmodified, so it's just this one. 7x minus 2 to the negative 10 plus, because it's product rule, the derivative, or the first, so the first is 4 minus 3x, 4 minus 3x to the fifth, times the derivative of the second. Well, here's the derivative of the second. So we need to put negative 70 in brackets, so it's not minus 70. 7x minus 2 to the negative 11th. Okay, we're good. Now, theoretically, some of you are proficient enough that you could greatest common factor this right away. I don't even have that confidence in myself. I know I could if I really put my mind to it, but if I do a quotient-ish rule using product rule, next step I'm always going to do is I'm going to drop those negative exponent things into my denominators. So we're going to have negative 15 bracket 4 minus 3x to the fourth over 7x minus 2 to the 10th, because it's now in the denominator. I'm going to still say plus negative 70 bracket 4 minus 3x to the fifth over 7x minus 2 to the 11th. Okay, now I'm going to get myself a common denominator. So my common denominator is going to be 7x minus 2 to the 11th. So I didn't give myself much room here, but I'm just going to save myself rewriting a whole other step. So I'm going to multiply by 7x minus 2 over 7x minus 2. Okay, and that's what we're going to do. So we're going to say that this is going to be, so negative 15 bracket 7x minus 2 bracket 4 minus 3x to the fourth, and then minus 70 bracket 4 minus 3x to the fifth. And I'm able to do that now all in one go because they have that common denominator of 7x minus 2 to the 11th. Okay, so do some simplification here. I'm going to greatest common factor. So greatest common factor of negative 15 and 70 is, I guess, going to be negative 5. And then, well, there's no 7x minus 2 over there, but there is 4 minus 3x to the fourth in common between both of them. So 4 minus 3x to the fourth. And I'm going to greatest common factor that out. So negative 15 divided by negative 5 is 3. There's still that 7x minus 2 hanging around, so 7x minus 2. The 4 minus 3x to the fourth, they're all gone. So they're all gone. Negative 70 divided by 5, I guess, is going to be positive 14. Well, divided by negative 5. And the 4 minus 3x, there were 5 of them. I took 4 of them, so there's one of those left. So 4 minus 3x, like that. And that's all going to be over 7x minus, that's why is that a superscript? 7x minus 2 to the 11th. Okay. Now, simplify. I'm going to distribute and gather my like terms. So we're going to have negative 5 bracket 4 minus 3x to the fourth bracket. So we're going to get 21x minus 6 plus 40, 56 minus 30, 42. So minus 42x all over 7x minus 2 to the 11th. Okay. And we're almost there. Well, this takes a lot of room. So negative 5, 4 minus 3x to the fourth bracket. So we got 21x minus 42x, so that's negative 21x. And negative 6 plus 56 is going to be plus 50. All over 7x minus 2 to the 11th. Now, strictly speaking, we could stop here, but it's not normally good practice to have a leading coefficient of negative inside a bracket. So I'm going to common factor out a negative 1 and bring it to the front, which is nice because that negative 1 from the brackets and this negative out here are going to cancel each other out. So we're going to have 5 bracket 4 minus 3x to the fourth bracket 21x minus 50 all over 7x minus 2 to the 11th. And there it is. Easy peasy. Okay, so that was a quotient-ish rule done as product rule. If you did it as a quotient rule question, yay you. Hopefully, if I didn't make a mistake, and here's hoping that I didn't, although it's certainly feasible, you should have gotten the same answer as me. If you are off there doing your work and you're like, oh crap, Galbraith, you screwed up, kudos to you. Shoot me an email or post it on Classroom, make fun of me. We're all good. Awesome. So product rule, I didn't really do quotient rule. Yeah, but we know how to do quotient rule. And so we also did some chain rule in there. So let's now start talking about some of the special case derivative rules that we need to know. So some special cases. Right, so special cases. So let's think about them. So certainly all the trig ones. So trig. So really, we're going to stick with just sine x and cos x as our trig. We could do tan x, but I'm not going to do tan x. I'm not going to assess you on that for sure, but we could do. So there's trig, and then we also did logarithms. So logarithms, there was, log base a of x, and then there was also the ln of x, okay? And then we did some exponentials. And within exponentials, we had a to the x, and we also had e to the x. Okay, so let's revisit some of those to kind of remind ourselves what's going on. So let's look at some of the trig ones. So imagine we'll just start with an easy trig. So some examples. So if we had a trig one, so imagine we just started really simple. Imagine that we did f at x is equal to, how about, sine of 6x cubed. And I want to know what f prime at x is. So I'm hopefully, you don't need me to keep reminding you, but by all means, pause these things. If we're going to be finding f prime at x, I'm going to be doing it in a second, and do it on your own and make sure that you get it right. Okay, so here we go. So sine, the derivative of sine, recall the whole trig one was the Santa Claus, negative Santa Claus, right? And that goes like this, like this, like this, and then whoop, and it comes back. Okay, so sine is going to turn into cos. So the derivative of the sine of something is the cosine of that same thing. And then we have to multiply by the derivative of that thing. So in that case, it's going to be 18x squared. So normally we're going to write that out front. So we're going to get 18x squared cosine of 6x cubed. Okay, lovely. Let's try one a bit spicier. So imagine that we had another one. How about if we had g at x is equal to cos to the fourth of 7x minus 5. So this one's a fair amount spicier. Go ahead, give it a whirl. Come on back. Okay, so let's do the derivative here. So we're going to have g prime at x equals. Well, actually, what I'm going to do is anytime I've got an exponent on my expression like this for a trig, I think it's a good idea to write it kind of like this so that it's obvious what's going on. So this is really the cosine of 7x minus 5. And that whole shooting match is to the exponent 4. So that means when it's written like that, it's a lot more obvious that this is something to the fourth. And we know the derivative of something to the fourth is 4 something cubed. So I'm going to differentiate. So we're going to get 4. And that cosine of 7x minus 5, it's not going to change, right? It's still cosine of 7x minus 5. And now it's cubed. But then I have to do the derivative of what's inside the brackets. Well, the derivative of cosine is negative sine of 7x minus 5. Okay, maybe put brackets like this. And then I have to take the derivative of what was inside the sine. So I have to multiply by 7. Okay, so there's the derivative before I've done any simplification. Let's do some simplification. So we're going to have 7 times 4 is 28, and there's a negative there, so it's going to be negative 28. And then it doesn't really matter whether I do sine or cos next. I'm going to do the sine of 7x minus 5 times cos cubed of 7x minus 5. Okay. So I think I'm going to stop there. I'm going to post these a couple videos, and then I will post a couple more videos with subsequent stuff. So we still got a fair chunk of stuff left to go. Okay, have a nice day, children.